In my previous videos in this series, we learned how to create and modify grease pencil shapes using Python. In this video, I'll show you how to use Python for animation and transformation. If you've been following this series, you know the drill about how to set up your UI for coding with grease pencils. Start in 2D animation mode, split the view, set the view to a text editor, and create a new file. You know, yada yada yada. Animating your shapes is a relatively simple process. To kick things off, let's borrow the code we used for the last tutorial for stars and spirals. To keep things neat, we'll get rid of all the functions except the star function. We'll also get rid of the calls to the functions we deleted. Then we'll test it out to make sure everything still works. Now we're ready to animate the star. We'll begin by creating a numFrames variable to control the number of frames we want to have. Then we'll iterate through that number of frames using the variable f to represent each frame in the range. In our previous code, we were just placing our grease pencil strokes in the first frame by explicitly referencing the first frame, frame 0. But in this case, we're going to create new frames by calling the new method on the frames Python object and use the variable f to indicate which frame we want it to be. We could also use the f variable to drive the x position of our star, but the values are a bit large, and it would send the star flying off the screen. So instead, let's create a new variable x and scale the value down to 10%, and then use that value to drive our position. This way, the star only moves 0.1 units to the right for each frame. Before we test this out, let's delete any existing keyframes, for reasons I'll come back to, and then run the code. Our star should now be animating across the screen. From here, we can continue to experiment with different values. Oh right, that. If we try to rerun our code, Blender is throwing a traceback. If we open up the console window to examine the error, we see that it's telling us that a frame already exists for frame 0. Blender doesn't automatically write over or add to existing frames when you're using the API, so we need to adjust our code to do so. What we want to do here is to check whether the frame exists, and if it does exist, we'll assign it to a variable and clear its contents. If it doesn't exist, we'll create a new one. But before we do that, we should probably tunnel down into the API a bit further to help clarify what exactly we're doing here. In my previous videos, I showed you how the grease pencil API was arranged in a hierarchy of layers, frames, strokes, and points. For each of the components we previously have been dealing with, there are actually Python objects in between them specifically made for handling operations on multiple subcomponents. These Python objects don't have a lot of methods on them. Mostly they can be used for managing the number of subcomponents, and in fact we've been more or less able to ignore them thus far. In this case though, due to the fact that there can only be one frame at any given position on the timeline, we need to carefully manage these frames in our code. What we want to do here is to check whether a given frame exists on our layer, and if it does, we'll simply reuse the frame. If not, we'll make a new one. We'll create a new function called getFrame. We'll pass in the frames object, and then the frame number we want to check for. We'll create the variable to hold the frame if it exists, and then we'll cycle through each frame on the frames object to see whether its frame number attribute matches the frame number we're looking for. If it does, we'll assign that frame to our frame variable and break out of our loop. And finally, we'll return the results of our search, which will either be the frame or nothing. Back in the main body of our code, we'll add a call to the getFrame function. If it found a frame number that matched, we'll make a frame object for our frame. Otherwise, we'll make a new frame. Now if we make changes to our settings, it gets rid of the traceback and just reuses the old frames. If we have a more intricate shape, like say a Suzanne grease pencil object, redrawing the strokes in a new position simply isn't an option. What we need is a way to apply transformations to any given stroke. By transformations, I mean translation, rotation, and scale. One way to go about this is to transform the whole grease pencil object. To do this, let's comment out the part of our code that deals with the internal grease pencil data and focus on the grease pencil object itself. We'll clear out the star shape, and in object mode, go to Add, Grease Pencil, Monkey to create a Suzanne grease pencil object. At this level, transforming the object is very simple. To translate the object to a different position, we'll set the object's location variable to a specific value. Similarly for rotation, we use the rotation Euler, and for scale, the scale attribute. This can be very handy when the entire grease pencil object needs to be transformed. but it's worth keeping in mind that when you use this approach, it rotates all of the strokes in the grease pencil. For example, if I reset my transforms and switch to edit mode and duplicate the Suzanne strokes, I still only have one grease pencil object, so if I try and rotate the strokes now, both heads are affected, which may not always be what you want. This presents us with a tricky situation. In the Blender API, we can transform our drawing high up in the hierarchy at the object level, but we can't transform any of the other intermediate steps in our hierarchy until we get to the stroke point level. That is, there are no existing methods for transforming an individual stroke within a grease pencil object. Since we can't directly transform our strokes, our functions will transform the points in such a way as to keep the points' relative positions consistent to each other, just transformed. To ease you into it, let's take a look at the simplest type of transform to perform, translation. Translation is an additive process that we've actually seen before in the tutorial on generating circles. In that video, I showed you how translating a point's position is simply adding the point's current position to the amount you want to offset it by. We'll do the same thing here, but put it in its own function so it can be used on any stroke we want. First, let's delete our existing grease pencil object and create a new monkey object. In our code, we'll clear out the changes for transforming the grease pencil object and uncomment the previous code. In using this grease pencil object, we also have a new wrinkle. It contains two layers, a lines and a fills layer. Therefore, when we transform this object, we need to do so for both layers. Just to keep things simple, we'll remove the bits that animate the frames and just do static transformations for the time being. Instead of working on the active layer, we'll switch it to a for loop that cycles through all the layers. We'll add another for loop that cycles through the strokes on each layer, and then we'll add a call to the custom translate function that we're going to create in a moment. We'll pass in a stroke and a 3-item tuple to represent the amount we want to translate it for all 3 channels. Now we're ready to build our translate function using the same parameters. Thankfully, this is pretty simple. Since translation is an additive process, all we need to do is loop through the points on the stroke and add our translation offsets to the existing value. As we've seen in previous tutorials, adding each channel together is possible, but it makes the code a little harder to read. So to keep things tidy, we'll use the vector class from the math library. If we now feed our call a value of 0.2 in the first slot, the monkey will now translate 0.2 on the x-axis. Super simple. Although translating an object is relatively easy, scaling objects is a bit more involved to do mathematically. If translation is an additive process, it seems logical that scale would be a multiplication process. That is, if we want to scale up the points on a stroke, we just multiply their current position by some value. So let's give it a try. Building our new scale function is super easy. We'll start by copying the translate function and then just changing our plus sign to a multiplication sign. Now if we put in a scale offset of 2 for both the X and Z channels and run it, the monkey scales up by 2. It can't be that easy, could it? Well, no, unfortunately. This method of scaling works in this case, but let's change things up a bit to show why it won't work in every situation. First, let's scale back the monkey to its original size. This brings up an important point. Since we scaled the monkey to 2, scaling it back to its original size should mean a scaling of 1, right? Nope. Our scaling function scales relative to the current size, so a value of 1 does nothing. To scale it back to the original size, we need to scale by 0.5. If I now switch into edit mode and select the strokes, and hit G to move them again slightly down and to the left, back in object mode, we'll now try and scale our object again. This introduces a potential problem with our approach. The strokes scale up, but notice how the monkey also moves down and to the left as well. What if we wanted our monkey to scale up from its center point? In order to do that, we need to take into account the stroke's pivot point. When translating points, the pivot point doesn't really matter. A point on the right side of the head and one on the left side of the head both move the same amount. But when we scale an object, the points move away from some other position. Unless explicitly defined, the points scale up from the world origin 0, 0, 0. This means that when the monkey's head is resting at world 0, all the points move away from the origin, which is what we want. But when the monkey's head is below and to the left of the origin, the points all move in a negative x and negative z direction. This introduces some potentially unwanted translation into our grease pencil strokes. To fix this, we need to introduce the notion of a pivot to our function. We'll start by adding a new parameter to our function called pivot and give it a 3-item tuple with 0 values. That means that by default our pivot is at the origin. To take into account the pivot during scaling, we need to get sneaky. We know that if the scale strokes from the world origin, the object doesn't pick up any translation. So what if we just move things to the origin, scale them, and then move them back? It's just crazy enough to work, and this is where the pivot comes in. The pivot is basically an offset from the world origin. If we subtract this value from each point's position before we try to scale it, we can avoid any unwanted translation. We do that in our code by introducing a new line in front of our existing line. In this line, we'll subtract the pivot values from the point's starting values. Remember, we're wrapping these in vector objects so we can perform the math. Subtracting the pivot from the point's position moves it back to the origin. Next, we add a line after our scaling to remove the pivot offset. This means that our point moves back to its original position, but with the scale that we've added in the previous line. Now we're ready to test it out. But before we do that, we need to figure out where we want our pivot to be. We'll create a fancier way of doing this shortly, but for now let's create an empty object by going to Add, Empty, Plane Axes, and then hit G and move it somewhere around the center of the monkey's face. If we then hit the N key to show the attributes, we can see the X and Z positions that represent the center we want to pivot him from. So we'll plug in those values into our call to the scale function, and voila, the monkey's head is now scaling from its local position. Of course, you don't want to have to create an empty to find the grease pencil's pivot every time, so let's make a function that finds the center of the object for us. We'll create a new function called getCenterPivot, and into this we'll pass our grease pencil object. We're using the entire grease pencil object here because we want to find the center of everything in our grease pencil object. When working on your own projects, you may decide to do this per layer, frame, or stroke, but in this case it makes sense to find the center of everything in our object. Our goal is to find the average position of all the points, so we'll start by adding a few variables, cx, cy, and cz, to hold the sum of the position values for each channel. We'll also create a variable to hold the total number of points. We then add some loops to get us all the layers, frames, strokes, and points in our grease pencil object. Since we're already doing that further down in the code, we'll borrow that to save some typing. Once we're down to the point level, we can add each point's x position to our cx variable, the y to the cy variable, and the z position to cz. We'll also iterate the num points variable so we can get a count of the total number of points in our object as we go. Lastly, we perform the averaging calculation on the way out the door in our return statement. We simply divide the channel's sum by the total number of points. And that's it for our function. Now we can add the call to our function in the main body of the code. Because this function examines the entire grease pencil object, we need to call it before we start tunneling down into the other components, and we'll assign the results to a variable. Lastly, we swap in the new pivot variable into our call to the scale function and test it out. Voila! Scaling from the local center. I've saved rotation for last because it's most complicated of the 3 transformations to set up. When translating a point, it's pretty clear what needs to be done to transform the point. Likewise with scale. But with rotation, it's not as obvious what we need to do to transform our point. If you've watched my previous videos on making circles, you may have noticed that we had a similar issue when drawing a circle. The solution there was to use the sine function from trigonometry, which allowed us to draw the line in a smooth arc rather than a straight line. The same goes here. If we can redraw the existing point somewhere along an arc, we can rotate the point. But there's a twist, so let's start building our rotation function to see what we're dealing with. Since we're going to need some trigonometry here, make sure that you're importing pi, sine, and cosine from the math library. Now let's start a rotate function as we did with the other 2. We take a stroke as the first parameter, and for the second parameter we'll take the number of degrees we want to rotate. First thing we'll need to do is convert our angle, which is degrees, to radians. This is because the sine and cosine functions want the input angle to be in radians. Not sure what a radian is, or a sine function for that matter? Check out my video on building circles where I go through the fundamentals of trigonometry and how to use it for circular objects. To convert our degrees to radians, we know that 1 degree equals pi divided by 180 degrees, so multiplying the number of degrees by pi over 180 gives us our answer in radians, which we can put into a variable called angle. Next, we need to pre-compute our sine and cosine values. We'll put each of these into their own variables. Now we're ready to start going through our points. For each point in the stroke, we'll start by splitting out each of the 3 position channels into its own variable x, y, and z. Rotating things in 3 dimensions gets very complicated very fast, so to keep things as simple as possible, we'll just focus on doing 2D rotations. To rotate each point, we're more or less moving our point around a circle in the direction we want it to rotate, and to do that, we'll use a trigonometry formula. For the x position, we'll multiply the cosine times x, and add that to the sine times z. For the z position, we multiply the sine value times x, and add that to the cosine times z. This formula might seem vaguely familiar to you if you've watched the video on making circles, but on closer examination there's something a bit weird going on with this formula. When we were drawing circles, we used the sine function to determine the z position of the point, and the cosine function to determine the x position. But here we're using both the sine and the cosine functions to define both of these channels. So what's going on? To avoid getting too far into the weeds of trigonometry, we'll just say that this is the formula for computing 2D rotation. But if you want to dig deeper into how this formula works, I'll include a link to an excellent Khan Academy video where it's explained in depth. With our formula in place, we've got everything we need to rotate the strokes. All we need to do now is to add a call to our function and pass in the strokes and the angle we want to rotate them. Let's say 45 degrees. That's it. If we run our code, our monkey head should rotate counterclockwise by 45 degrees. It rotates counterclockwise because the mathematical conventions for the sine and cosine function move in that direction. But intuitively, it might make more sense if, when we rotate in the positive direction, it rotates clockwise. To do this, add a negative sign to the sine function in the second formula. But there's one more problem to solve. Just like the scaling function, if our strokes are away from the origin, rotating them causes the shape to translate too. So we'll need to add the notion of a pivot point to our rotate function as well. The idea is pretty much the same as we did with scale. We move the points to the origin, rotate them in place, and then move them back to their original position. Since we've already figured out the pivot point in our main body of the code, let's pass that pivot point to our rotate function and add it as a parameter. Next, we'll split out the pivot's channels into their own variables, just like we did with the point positions. Below that, we'll add 2 new variables, adjusted x and adjusted z. For each of these values, we'll subtract the pivot's position from the point's original position. Like before, this moves the points to the world origin. Down in the lines where we set our translation values, we'll modify our formula to switch out the x and z variables with the adjusted x and adjusted z variables. This allows us to rotate the point around the world origin, and then we'll add back in the pivot offset at the front to move it back to where it was. Now, even though our monkey strokes are away from the origin, the monkey rotates around its center. Nice. Now that we know how to animate objects and transform them, let's try and combine the 2 processes. We'll bring back our code for animation by adding the for loop that steps through the number of frames we want to create. Remember, we want to affect all layers, so we'll add it inside the for loop that we're using to cycle through the layers. We're using our getFrame function again to help us test whether a frame already exists. When we were animating the star, if the frame didn't exist, we would just create a new frame and build the star where we wanted it. But this time we need to copy the contents of the first frame so we can transform it. To do that, we'll call the getFrame method again, but this time we'll grab the previous frame by passing in the current frame number minus 1. Then we'll make a copy of that frame by using the frame object's copy method. This creates a new frame that's a duplicate of the previous frame. We'll then go through all the strokes in this new frame and rotate them by 10 degrees. And there we go. It's worth noting that the copy command only copies the frame to the next frame by default. If we want to copy our frame to a specific frame number, we have to copy the first frame, then set the frame number attribute on that frame to the one we want. For example, if we wanted to animate the rotation only on every other frame, we could add a test against a modulus of 2, and then make sure we're using 2 frames back for the frame to copy. And lastly, after we copy the frame, we set its frame number attribute to the current frame. This moves our keys so that we're only keying on every other frame. We now have all the tools we need to transform and animate our grease pencil strokes using just Python. It's It's worth pointing out that there are many ways of doing transformations, but I chose these methods because they seem the easiest to implement and the simplest way to present the concepts. Plus, they seem relatively efficient. I hope this video has been helpful. If you've enjoyed this series so far, make sure to like and subscribe so the algorithms stop ignoring me. Thanks for watching.